start with like brief introduction and subject. Definition. So Hodge structure of weight n. For vector space over Q or Z model of finite rank. Rank V as the decomposition of computation of V as a direct sum was equal to n VPQ with condition when VPQ bar or conjugate is the same as VPP. So it's like well-known case of Hodge structure for n. Let me briefly recall a couple of facts. So fact number one, so if you work with Hodge structures with weight 1, integral Hodge structures. So they start with Z model of finite rank. When it's the same as the complex product. So the simple way to observe it, so we have V is in the classification, and this is the basis in V1, 0. And so the quotient is the torus. Vice versa, if you start with a complex toroid, so Cn quotient by gamma. When we can think about this Cn as a like gamma real endowed with almost complex structure, and consider decomposition of gamma real by gamma real 1, 0 and gamma real 0, 1. So it's like way to identify complex toroid with Hodge structures of integral Hodge structures of weight 1. The second fact is the formula when we have polarization when it's the same as like this one. This is 1b. So for polarized Hodge structures of weight 1. Is the same as the Abelian variances. And the first fact, when we have, you can think about Hodge structures of any weight is a real algebraic representation. So, so for element V from V to Q, is action of rho Z on V is just multiplication of Z to the pi, Z bar to the Q of Z. So it's like and if it's a element is real, just multiplication by t to the n, when n is p plus q. Okay. So let me recall a original Kubis attack. So first of all, we have the Hodge structures of K3 type. So what is it? It's a Hodge structure of weight 2. And VPQ is like 0 if p minus q by modulo bigger than 2. And the dimension of v to 0 is 1. And complement. And the same for 0 2 by definition of Hodge structure. So when this is called the Hodge structure of K3 type. And so we know that where exists a Kummer K3, so if we start with torus, complex torus, we can construct a Kummer K3, just take a quotient by involution, and we solve 6 integralities from which you get. And this gives us a way to obtain it from a complex torus, so with the same integral Hodge structure for one, K3. And sure, K3 has a Hodge decomposition of K3 type. And so Dubus type construction is a way when we start with K3 type Hodge structure and we get complex torus. And in the case of polarized Hodge structure, we can obtain bigger. Okay. So let me briefly explain what happens. Like that. The key object of this construction is a Clifford algebra. So, K3. So it's like two-dimensional complex. So this complex surface with trivial canonical bundle. So with intersection form, it defines Q. And then we consider the Clifford model for second homology and the intersection from Q. So this is quotient of tensor algebra by ideal, which is formed by V tensor V minus V. So for this Clifford model, we have natural z by 2z grading. So we have even part and odd part. I think. And to get so now we'd like to starting from K3 type Hodge structure, we need to get a torus, and this torus, so by this correspondence, so we need to obtain a Hodge structure by one, and we will use this the lim torus notation. So let us consider the view. So it's just intersection of our decomposition with with video. So it's like we have a natural decomposition on the view too. If you have a decomposition of the type. So it's view 1 intersect with the view plus v2 0 plus v0 2 and intersect with the view. And so we know what this K3 type Hodge structure. So 2 0 parts is one-dimensional, 0 2 parts is also one-dimensional. So we can take a generator of 0 2 part. So sigma is a generator of 0 0, and such that pool of Q of EI is 1. So when we get this basis E1, E2 is autonomous basis and technical homology. And we can consider the element G. So this is J is like E1 times E2. When the first fall E1 times E2 is equal to minus E2 times E1 in Clifford of the video. So let's say what it is B here. And second, so we can consider with J with element E1 times E2. So it's like, so J induces complex structure on the effect of E. So the first thing with J preserve z by 2z gradient of a Griffith model. So preserve both even and odd parts. So plus and the last one with J doesn't depend on the choice of places you want to do. Okay, then we have so like two isotactic Koch structure is a Koch structure of like one. On a Griffith plus of D, given by so this is representation from C star to JA of Griffith plus review, and X plus I Y goes to X plus J Y. So this one is like a real algebraic representation, and it gives us, like by definition, a Koch structure of like one.
You mean multiplication by that?
Yeah, multiplication by that. So if a Koch structure, like if we start with an integer homology, like with the model finite rank of K3 type, when with K3 type Koch structure, when we have the following: when Clifford plus of V is lattice here, so lattice, and we can take a quotient, so like 2 isotactic torus is Clifford plus of VR, quotient by Clifford plus of V. Okay, so everything what we need to work with just non-polarized, just some Koch structure of K3 type. So we need this intersection form on the second level. Okay, so we know what K3 is. It's first example of hyperkähler manifold. So it's Gromov symplectic manifold. Let me recall the definition of this hyperkähler. So we start with Riemannian manifold MG.
You could have done this with a degenerate Q, right? The only thing you really needed is that Q is non-degenerate.
Non-degenerate, yeah. We need
on that particular vector, right? But it could be degenerate on other vectors.
Yeah. That's right. So we have with a Riemannian manifold, we have three complex structures I, J, and T. Spine quaternion relations. And as compatible with metric, and corresponding Kähler forms are closed. So where I mean omega I is just for two vectors x, y. This is G of x, I, y. Okay, so this is so when M is called another way to think about this manifold, so we can think about the Goldman group. So the Berger theorem of classification of the Goldman group, and the Goldman group subgroup of a simplectic group, when we have also hypercurrent manifold. But I think I don't need it today.
The interesting bit of trivia is that these manifolds were invented in a room on the hallway in a North Wing.
Yeah, maybe, so I don't want to talk about the Goldman group. It's like more or less differential geometry, but the thing between it is what hypercurrent manifolds were homomorphic simplex manifold. So it means that there exist homomorphic 204 such that like n power of it is a section of n-canonical twice. So this form could be constructed. So let's start with complex manifold M with complex partial I. When this omega 204 in respect of its complex structure is omega j plus I omega j. So this is correct defined. And this is 204. And we will need it. So this, so important to think about hypercurrent manifolds. So that second homology also have K3 type. So 2-0 part is one-dimensional, and it's generated by this form omega capital. So let me say it right. So it's for simple hypercurrent. Yeah. So simple hypercurrent manifold is such manifold when 2-0 part is generated by one form omega and it's simply connected. So starting from this point, I will talk about on the simple hypercurrent manifolds. And by Bogomolov theorem, like in hypercurrent case, Bogomolov theorem by more general case, by Witt-Bogomolov. So we have the composition of any hypercurrent manifold. So any hypercurrent manifold is covered, finally covered by a product of simple ones and torus. And K3 is a basic example of hypercurrent manifold. So I have an hour, yes? Yeah. So let me briefly recall like all 4 known examples of hypercurrent manifolds. I mean, 2 of them, and we'll just mention what exists like 2 more. So the basic one is Hilbert scheme of K3. So you take a symmetric n power of K3, and we need to resolve the singularities. So one can check what is simply connected, and it's so the simple hypercurrent manifold. Second example. So this example exists in any dimension. I mean, in any even complex dimension. Second one is generalized Kummer. So we get one from K3 is the K3 itself, and generalized Kummer variance is so we start with torus, for example. Consider the Hilbert scheme of n plus 1 point in torus. So the 0 dimension, we can think about like 0 dimension subschemes of the following length. And we have map to, like Albanese map to torus. So just a summation of coordinate on the product of torus and induce some map for the Hilbert scheme to torus. And here's a 0. And this map is sigma and pre-image of 0. Simple hypercurrent manifold, which is called generalized Kummer. And there exist 2 more examples of Grady, constructed by Grady, so in dimension 6 and 10. So I will not give a definition of them, but if you know it, like you can start with a modular space of semi-stable shifts of rank 2, some numerical condition on chain class. We need to quantify this and resolve singularities. And likely in these two cases you have new hyperplane manifold. The manifolds are different, which are different from this one, information are different. And for example, like important invert is the second place number. So for the Hilbert scheme, this is 23. For Kummer is 7. For 6-dimensional grid is 8. And for 10-dimensional 24. And 23 by 21, 22 plus 1, so 22 for 43. And we have one more.
Another bit of trivia is that the 6-dimensional example is invented in this room.
Yeah. Okay. So we can, like the first observation, we can work, we can apply classical Kubis attack construction for these hyperplane manifolds because of K3 type Hodge structure on the second homology. So it also looks like 1, so something between -2 and 1. And you can get some torus. But actually, so dimension of the torus depends on second basic number. So for K3 we have 2 to the 19, so is the dimension of this Cook's attack variety. And in this case it depends on B2, so it's like 2 to B2 minus 1 like it. And but what I think with these examples were high dimensional, and they exist like high homologies. And what happens with high homology part of hyperplane manifold when we apply Kubis attacking? But for classical one, nothing happens because there's no embedding of all homology algebra to homology algebra of torus, high dimensional torus. But we can generalize Kubis attack construction and get a good embedding of all homology algebra, preserving the Hodge structure and some additional structures in the homology. So first of all, so like now we'll talk about homology algebra of hyperplayers. So I'll mention a couple of very important facts about it. So, so let me define actually Fabinius algebra. So I have A from 0 to n. So it's a great cumulative algebra such that dimension of last element of the iteration is 1. Then consider the following mapping for 2 elements x and y. We consider projection of x product x y on a to the 2n. So because this one dimension, so it's well defined, and if it's so we're pairing is non-generate, when A is called a Fabinius algebra of degree 2n. Okay, so the first of all, the homology algebra of hyperplane manifold is a Fabinius algebra. But moreover, on Fabinius algebra, we can define Lefschetz triples. So let us take some eta on element of gradient 2 and consider 3 operators. So the first one is eta is a multiplication by eta. So we have sigma, which is restricted on element of degree I, is just multiplication of I minus n. So we have, this is 2n. So this n is half of dimension. Then we can construct lambda eta such that with free from asymptotic people. But this one is there is the open condition on two form. So when we have, so we can consider, like this is Frobenius-Lefschetz algebra, when we have Frobenius algebra of Lefschetz triples, and we can consider the Lie algebra generated by all asymptotic triples for all like two forms. And this algebra for hyperclear manifolds had been studied by Lunz, Wang, and Verbitsky. So M is simple hyperclear. So A button is Kagamoji algebra. So total Lie algebra is Lie algebra generated by all asymptotic triples. When this algebra is orthogonal Lie algebra, so it's isomorphic to SO for B2 minus 2. So we have action of this Lie algebra, Kagamoji algebra, and this action comes from the following. So, let me use this part. I'll come back to this to this diamond a bit later. Okay. So why it's like 2? So we have first of all we have Q. So hyperclear manifold were high-dimensional, but still we have some form, non-generate form on the second homology. And this form is really important for us, and this form is called Bavit-Bogomolov-Fujiki form. So could be defined by Fujiki theorem, for example. So M is simple hyperclear. Of dimension 2n. When we have, when they exist, integral, primitive, not degenerate, quadratic form Q, on H2M and rational constant C, like say lambda, such that for any two forms eta, we have the following. So integral by eta to n is the same as lambda q. So to get the integral of any two form, we need to compute a value of quadratic form on this two form eta to the n and multiply by some constant, which is called Fujita constant, and it depends on manifold. So factor q has signature 3 b2 minus 3. And is you can see we have 4 b2 minus 2, so it's not a miracle. So let me define this Mukai extension of H. So we have H bar. So second gamma we have H0 plus H2 plus H4. So we have elements of gradient 0, gradient 2, gradient 4, and we have form Q bar defined on this triple, two triples. Such that restriction of form Q tilde on H2 is a form Q which is by equal homomorphic form. And so we have Q of x prime plus a b prime plus b a prime. And now we can see that there's H0 and H4 part waveform hyperbolic lattice in respect of with from Q tilde, and this hyperbolic lattice has signature like 1, 1. So an important step of doing this theorem is just we have action of so we take Lie algebra directed by O's into triples, and we study action of with Lie algebra on H tilde, and we know that orthogonal Lie algebra on H tilde Q tilde is just so for beta minus 2, and we need to prove that this one need to prove that this action is so with two Lie algebras were just isomorphic. Okay. And so I forgot to say that we exist. So in this Lie algebra, we have an array of elements, wave operators. So it's just multiplication with complex charge I. It's just multiplication of square root of minus 1, p minus q on pq form. And the weight decomposition in respect with wave operator is the same as Hodge decomposition of the Riemann algebra. Okay. So now we definitely can apply the classical Hooke's effect. So first, I mentioned a couple of minutes before when they have classical Hooke's effect for hypercarrier, but this is not it was almost true because we need to have some quadratic form on second homology. And now we have this form by equal homomorphic form. So the H2 part is 1, P2 minus 2, 1, and we have from Q here. Okay, and we know, so important category of with Van-Loon's theorem, but cohomology algebra of hypercarrier manifold is just sum of reducible models in respect of reducible models of reducible SO for P2 minus 2 models. So now we can define generalized quick stack embedding. Of cohomology. And let me say later what they mean. So we start with like H with quadratic form Q. So for us it's just second homology of Barry-Bogomolov-Fujiki form. And we can start with the same Clifford model, a Clifford algebra for it. And we have Z by 2 the gradient. So let me say just for simplicity, just see card. Okay. So first of all, some algebraic structures on this Clifford algebra. So we have alpha from C to C. This is just a Clarice involution. And beta from C to C opposite is anti-involution, anti-aftermarket induced by the form. So we have V1, tender, so on. Vk goes to Vk, tender, so on, V1. So we just change the order. And this operation induces anti-automorphism of the Clifford algebra. And for any A from C, they can define A bar, which is just by definition alpha bit of A.
What is the parity involution?
I mean just from C0 to C1. Which is the
Oh.
So it's the standard. And
so you're using the structure of the Clifford.
yeah.
It's not on any Z gradient.
Yeah. So now we have like, let's make a definition. So the bilinear form B is called Clifford invariant if B for A U V so let me sorry. Okay, is B U A bar V. So what is like A U V? So A is element of Clifford model, and U and V just elements. So with bilinear form on Clifford model, like left Clifford model V, and with U and V from V capital. So we like that we have some bilinear form when it's called C invariant, when we have the following one. Okay. And we have like a special form which is called trace invariant form. First of all, observation. So we have S1 of HQ, which is isomorphic to the amplitude of H, and is naturally embedded to Clifford. So embedded is the following. So for X, H, Y, it goes to 1 over 2 X, Y minus Y X. And the second, so consider Clifford model, Clifford algebra as a left C model of itself. So when they exist invariant symmetric bilinear form on Clifford. Okay. And this form defined as follows. So it's from tau for two elements u and v, which is just trace of u v bar. So we consider this u v bar is endomorphism of Clifford, and we have a trace of this element. The position with form tau is symmetric. C invariant. So sure, we need to check it, but it's like simple computation of Clifford algebra. And a bit more hard, but this tau is noise generator. And starting from this form, so this form is called invariant trace form, so tau. Okay. And now we can construct the embedding. So we have H, we have Q, which is Bogomil-Fujiki form, and the embedding is the form. So HQ is like all our data, and C is a Clifford model, like above. Clifford algebra, and V is a C model. Just any Clifford model with not any of dimension 4n. With C invariant symmetric bilinear form tau. So it's like all given data there. So then we can, after a couple of minutes, we can start with V. So when embedding is the following one. So phi from H to lambda 2 V star is the following. So x goes to omega x, defined as tau x uv. So from the property of this form tau x, symmetric bilinear C invariant form, we need to check with omega x is an element from here. So it's a simplification, you need to check it. And the question, natural question, what is the image of H on this lambda 2 star? Maybe use this space. So we have H, it advances lambda 2 star. It's here. And H is element of H is second homology, so it's part of all the homology algebra of Hypercurrent manifold N. So we just construct embedding of second homology to lambda 2 phi star, where V is just left C model or left model of Clifford algebra constructed by H, and Q, where Q is by Bogomil-Fujiki form on second homology of Hypercurrent manifold.
H is
H2.
2 of
Hypercurrent. Simple hypercurrent. And Q is by Bogomil-Fujiki form.
Thank you.
Yeah. And this is embedding. So tau defined on a Clifford algebra is given here. Is just trace of UV bar as an endomorphism of Clifford, and V bar. So V bar is alpha beta of V, where alpha is a parity involution on Clifford algebra, and B is isomorphism induced by changing the order of elements and tensor algebra from when V1 tensor Vk goes to Vk tensor V1.
Reverse multiplication.
Yeah. Okay. So first question: what is the image of H and lambda 2 star? And what happens with Oka-Gamoji algebra of simple hyperkern manifold, and what is correspondence with this model V? And we'll construct a good model V in a couple of minutes. Like the theorem. Okay. Let me like purpose proposition. Start with definition and definition. So V is a vector space. Is 4n-dimensional vector space when omega in lambda 2 V star in k-dimensional subspace. K-dimensional subspace is called k-symplectic structure. If the following conditions hold. The first one, so for any non-zero form omega, we have two possibilities. A rank is maximal one, and a rank is half-dimensional V. So it's like this condition applies with all degenerate forms from the quadratic in the partialization of forms the quadratic partialization of this space, and the second one is quadratic U. So
what's capital omega?
capital omega is k-dimensional subspace of lambda 2 star. Just some k-dimensional subspace. When
linear subspace, which is
linear subspace and this. Okay. So when it's called k-symplectic, if the following holds for non-zero forms from omega. So the quadratic of so we don't need like quadratic of degenerate forms is non-degenerate. An example, we have two symplectic structure. It means that it gives us decomposition of V is a direct sum of V1 plus V2. So it means so what's the two-dimensional structure? It means P of omega contains we have two forms, omega 1 and omega 2, and we can say what the kern of first form is omega 1, kern of second form is omega 2, both of them are n-dimensional, so we have two n-dimensional with 4 n-dimensional. So it gives us a splitting of our vector space into vector subspaces, and vice versa. Three-dimensional structures were studied by Hitchin, and we know hypersymplectic structures, and also studied by Verbitsky and Jardy. So the interesting thing, the proposition was the image of H in lambda 2 star is k-symplectic structure. It's just interesting, but maybe not so important for today. And more interesting thing, let's say, let's denote this image. So, double V is an image of H, of second homology, by this map. So when for algebraically closed field we have, so let A bar be some algebra generated by W, so the algebra in lambda bar is star generated by W, and so where V is a Clifford model over H with positive from Q, when this A bullet is isomorphic to so let's say F and H. So this is algebra generated by second gamma of hyperplane manifold. So algebraically speaking, with algebra generated by second homology is given by the following proposition. So algebra generated by second homology is isomorphic to the quotient of symmetric algebra by the following ideal, so x to the n plus 1, where q of x is 0, reduced by Vipple homology form. So it means like up to middle we have embedding of symmetric k power of h2, 1 of h, to the even homology group. And it's up to middle, and like
What's the rank for H? Is it 2 or 4?
yeah, this is 2. It's like this is the second homology. H is second homology of hypercarrier.
Maybe it's the dimension of the vector space.
It's whatever the second dimension is.
Yeah, second. Yeah.
That's not in or whatever.
No, n is the dimension of the hypercarrier.
Yeah.
Yeah.
Yeah. And K is like
So 4n is the dimension.
4n is
for dimensions hypercarrier. And so up to middle we have embedding of so with H2 we have embedding of symmetric square of H2 and H4 and so on up to middle, and after middle in the Hodge diamond we have so some correspondence. So let's say so like F to n plus 2I of H is isomorphic to symmetric n minus I of H. So it's like just a correspondence, like the usual mirror correspondence in a Hodge diamond of hypercarrier. And this is known for a long time. It's proved by Verbitsky, but this one by Bogomolov. But anyway, so the important thing what we have this W here, which is just the image of H of second homology, and with lambda 2 of V star, where V is a Clifford model, and we have A bullet, which is generated by WV, and it's here. Okay, but it's not true that all homology of hypercarrier manifold are generated by the second one, because there exist primitive forms. It's even not true for like generalized Kummer of dimension 2 or dimension 4, and copy dimension 4. And it is sure it's not true for gradients and so on. So, but we have this embedding for
What
any
is
Clifford.
V
Yeah,
again?
sorry. Sorry?
I'm sorry that I missed so much from the beginning. Could you tell me again what was V?
V is a Clifford.
Any Clifford model.
Any Clifford model of dimension 4n. Just
Has
any.
nothing to do with the geometry of the manifold?
No, it's yeah, it's just algebraic structure coming from. So Clifford model based on second homology of Q. So like all structures here.
But 4n is the dimension of X, not the dimension of the column. Has nothing to do with the dimension of H?
No, I mean we'll see later. But this Clifford model is just like dimensions divisible by 4. So this one is important.
So this n is not the same as the other n. We were saying.
Maybe it's confusing, yeah. But it's not, it's not the same, sure. Sorry. Let's say, yeah,
Okay.
This is important, but.
Yeah, but like in the standard Kugasatake, the Clifford module will be just the even part of the Clifford
Yeah.
algebra. So it's going to be 2 to the 19 or whatever.
That's the rank. So the M is going to be something like
Yeah.
that.
Yeah.
Yeah, so I have like 2 minutes, yeah?
Yep.
Wait.
Three.
But, still we don't have any embedding of all Kagamoji algebra on this with model. With no map. So we have this embedding, just explicit one. We know what happens with part generated by second Kagamoji, but not all Kagamoji algebra generated by second Kagamoji. And the theorem, so is what the main theorem. So it's work with joint of Nishirovitsky and Reisov. Maybe I have like one so Lasenko, Reisov, me. The theorem is the following. So for any quadratic vector space H from Q, any representation W of SO H tilde Q tilde. So this is Mukai extension of H, the usual one. Where exists a Clifford model V with invariant symmetric bilinear form tau, such that lambda body 3 star contains W as, let's say, SO H tilde Q tilde submodel. So when the Un's theorem, we know that the Kagamoji algebra of hyperplane manifold is the sum of reducible models in respect of this Lie algebra, and now we have a spec. By this theorem, we can construct a special Clifford model V. So here we have just an arbitrary Clifford model, and now we need to get a special one to have this embedding. So let me briefly explain what is the ideal of Clifford theorem. So,
but the embedding is now not canonical because on each reducible one
it's
space you can scale.
Yeah, it's true. So, first of all, consider V1 is a Clifford algebra as left Clifford model of itself. So when we have action of SOH tilde Q tilde on lambda body V1 star. So you need to check it. When we can consider spin of H tilde Q tilde, so it's double cover. So it also we have action of this Lie group on lambda body V1 star, and so the first thing we need to check is action. This action is fully faithful. So to do this, we need to prove that center acts non-trivially. So let us assume that W is irreducible model, first of all. So when we consider this the algebra, okay, so center acts non-trivially, we need to check it. So center of this group depends on a parity of H tilde. So it could be -1, which sure acts non-trivially, or maybe for even dimension case be more complicated, but still we have non-trivial action of center, so action of this Lie group is fully faithful. And then by the Lin-Milne theorem, any reducible representation, so like the Lin-Milne, so any reducible representation of this spin h tilde q tilde is contained in lambda lambda valid with star for some big n. So it's like so n should be like big enough. So if we consider like non-reducible model, when we consider with the sum of reducible models apply this construction, but this one is really like high-dimensional. Okay, in the last, maybe sorry to be like late, so but in the last minute, let me just state the last theorem. So we have M is hyperheader manifold, simple hyperheader. When there exist integer A and embedding psi from H from the homology algebra over C to homology algebra of torus. So here we have y plus A, so with A is a constant. So with embedding of G models and for any and for any complex structure Y I of HK type, hypercarry type, where exists a complex structure on torus. So such that this psi isomorphism is a morphism of Hoche structures. So so it happens. We take exact homology H, apply this embedding. By this theorem, we have a good Clifford model, and such that we have this embedding. When naturally we have embedding of the part generated by second homology algebra, and by the image of second homology algebra, and then one need to check that this embedding preserves a Hoche structure. But to check it, we need to recall that Hoche decomposition is the same as weight decomposition by weight operator in respect of this complex structure I. Okay, and A here, so the difference in dimension of our manifold M and the model given which we construct in this theorem. So it should be some. So the torus is a big dimensional, and this A is quite big, because dimension of torus is like super big, and dimension of manifold is somehow small. Okay, so let's go. So I'll run out of time, so sorry about that.
Thank you.
Yeah.
So in this last theorem, is the embedding giving you, is it isotypic? Can you reconstruct the image from the Hoche structure from the weight one Hoche structure on the target by breaking it into representations?
Yes. This is an important one. And another one. So I didn't talk much about periodization, but periodization is also so we can work with periodization.
So it is a complete analog.
Complete analog of yeah. And yeah. I know.
So is there a geometric case where you can show us what would the most efficient embedding look like, other than
No. Even in classic groups attack, we have like 2 to the base number dimensional torus.
Yeah.
Yeah, so big. But here you have a much bigger, so it's a construction for existence. Yeah. So even for 4-dimensional hypercradles, it's somehow something big. But
So what do you get for if you just run this for
this is a question.
for the Bourvil thing, the symmetric product,
Yeah.
and the Hilbert scheme?
The Hilbert scheme, yeah. I'm pretty sure we can do it, but we didn't study it. So it should be some explicit activity, yeah.
Should be somehow an abelian variety related to the usual Kubrick.
Yeah, exactly. Yeah, moreover, in the case of Hilbert, so the Hilbert scheme 2 points is like some special example, because cohomology algebra of Hilbert scheme of 2 points generated by second cohomology, because there's no primitive forms in the fourth cohomology. Yeah. So it's like very important fact, and for this example, I think it should be quite simple. So it's just related to the usual, maybe some product.
It would be interesting to see this for the more exotic exam, for example, one that Saka.
Yeah, sure. So the origin of our work was the following. So we need, so we would like to construct generalized Bavit Lagomov-Fujiki form. So some form on even cohomology. And the idea was so embed the cohomology of hypercradle, the cohomology of torus. So we can construct a couple of good forms. Important thing, we need to prove that these forms were non-generate, and this is hard. So nowadays we have like analog of Bavit-Lagomov-Fujiki form of fourth cohomology of 6-dimensional hypercradles, and already we have 6-dimensional gradient, so we can work with it. It's some cohomology structure, and moreover we can try to apply this new form to obtain some restrictions on cohomology on weighted numbers of hypercradles. But still I'm not knowing which examples could exist.
Do you get more interesting examples of these generalized Kugasatake abelian varieties that are given by geometric constructions, like the Paranjapa example for the usual Kugasatake?
I mean, I can be the leading one, yeah.
Yeah.
Actually, no, but if you would like to, so additional Kugasatake was used for some like arithmetic, like for the study of K3 or final fields, and so it's like with so we can lift our K3 or final field to a K3 complex K3 by the Lie and then apply this Kugasatake, and it works, and hopefully it will work also in this case. So what we think about this?
No, I was asking more about the geometric constructions, like if you take a Kummer K3 and take the Kugasatake, right? It's a power of the abelian surface. Or if you
this
take,
here should be the same. Yeah.
if you have one of these Paranjapa example, K3 with the Picard number 18, then the Kugasatake is a power of a 4-dimensional abelian variety.
Yes.
It's a 3.
Yeah.
Right? And
So
I think these are the only 2 examples when the Kugasatake, the usual Kugasatake.
Yeah, this is like
power.
exactly. Yeah. Exactly.
And
yeah.
but maybe for these guys you get more guys that are powers.
Yeah, I think so.
Because they're
No, it's very often powers. It's just that the power will be lower. If instead of rank 18, it has rank 17, 16, 15, you just get lower powers.
the power of something.
No, the power of torus.
Of
Torus.
something that's reconstructible, right?
I mean, that something would be a Kugasatake of.
Yeah, it will be a Kugasatake
Of Kugasatake of some-
of some
Yeah.
hot structure. Yeah, but no. I mean, because this is about. There were these examples of the bar about constructive Turelli for 4-dimensional Kummer, generalized Kummer varieties.
Yeah, so it's slightly different, but it still have like copies of this story, like a bit of variety. Yeah.
Okay, well, thank you again.